In this video, we're just going to finish up talking about heat of fusion and heat of vaporization. So I left you with this kind of graphical display of the changes in potential energy necessary to go from a solid to liquid and liquid to gas. And remember that these changes in potential energy are kind of what define these major changes in like the actual state of matter. And they have completely different characteristics, right? It's kind of like solid, 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 liquid, right? And then once you're liquid, you behave very differently from a solid. And I mentioned that the heat of vaporization is bigger than the heat of fusion. And one way to see that graphically is kind of my dotted lines here are around the amount of energy you needed to add. So the number I used was like 2 to go from solid to liquid. And I don't really want to attach a number to it, but like this amount of energy added kind of corresponds to that amount of energy added. And this amount of energy added corresponds to this amount of energy added. And you can see that because the change in potential energy from solid to liquid isn't nearly as big as between liquid and gas, it's going to take a lot more energy to make something go from a liquid to a gas. And again, you can kind of get some intuition about this if you think about what you actually have to do. So in one circumstance, you have solids in a crystal structure. And again, I like to think about that as kind of these molecules connected by springs, right? So they have a rigid shape. And they can vibrate around, and kind of the more energy they have, the faster they vibrate. But they're all kind of connected, and they're not going to switch order on us or anything weird like that. They have a rigid shape. And we need to add energy, right? And they're very stable, so they have a very negative potential energy. And now if we keep adding energy, right, they're going to keep vibrating more and more. So maybe these guys are vibrating more and more. But there's kind of a limit to how fast they can vibrate without breaking the spring, so to speak, right? And if you add enough energy, you can break that kind of rigid bond between them, right? They're kind of all locked in place, and you can start to break down that crystal structure. So instead of being this kind of rigid, organized structure, they'll be close together still. But now they might, and they're still going to attract each other. So they'll still stick together, and they're not going to move around however they please. And they'll all kind of just maybe kind of like, this one might go over here, right? But none of them are going to go crazy and fly out somewhere. They're all going to kind of stick together. And the difference between this and this, it's noticeable, and it's a pretty big change qualitatively. But the amount of energy to go from here to something like this, where you have these gas molecules that are just zooming around, right? They've broken the intermolecular bonds. They're not even really close to each other anymore, and they're just flying around. And remember, these molecules, when they're liquid, they're still attracting each other a lot, right? They're still pretty stable. They all kind of stick together and they flow, so they can kind of wiggle around and move by each other, but they're kind of glued together by that attractive force between them that we talked about earlier. And to take one of these molecules and completely kind of rip it away from all the other molecules that are attracting it takes a lot more energy than to simply break up the crystal structure of a solid. I mean, they both are pretty important, but it would take more energy generally to go from a liquid to a gas. And one thing to remember is that when you do go from a liquid to a gas, it took all this energy to make the liquid into a gas, right? It took the heat of vaporization, right? And this is generally in joules per gram. So like how much energy does it take for 1 gram of this substance to go from a liquid to a gas? And same with the heat of fusion, but for solid and liquid. And when you go from liquid to gas, it takes a lot of energy. And you can think of it as it has to absorb a lot of energy from its surroundings, right? And in our case of our graph, we're kind of assuming that we're adding energy. And so it's also true that if I'm going from a gas to a liquid, right, you're going from kind of 0 potential energy to this -8. So you kind of have lost energy, right? Where does that energy go? You have to dump it back out into the environment. So when gas condenses back into a liquid, it releases an amount of energy equal to the heat of vaporization. And this is why steam burns are especially bad.